Hey guys, Greaves here. Let's continue what we were doing last week, right? Which is still investigating what happens when light goes from one medium to another, okay? So now let's just draw something out, okay? So here's a surface, right? I have the reference table here. Let's just pick something out. Let's just say this is corn oil, right? Here's corn oil. And I'm picking something out here, right? Let's go zircon. This is a good one, all right? Zircon. So let's just say, right, I have a ray of light, which is starting in corn oil, right? And it's going to come down looking like this, and it's going to hit the surface, and I want this to hit the surface at 90 degrees, right? By the way, hit the surface perpendicular, right? By the way, now let's be careful for a second. It's coming at 90 degrees, right? Which makes it perpendicular. But let's call back with reflected rays, right? When we talk about reflected rays, we're talking about from the normal, right? So believe it or not, even though I am perpendicular, which really is 90 degrees from the surface, we're really on the normal, right? And remember, right, so this really is coming in at 0 degrees, right? It's coming in at the normal. Why is that? Because when we look at reflected rays, right, so let's just take a look at something like this, right? When I looked at reflected rays, right, we always measured with respect to the normal, right? So it comes in whatever made up angle this is, right? And it's going to bounce off at whatever made up angle that we just made there, right? So this one I'm being real specific. I'm saying it's coming in at the normal, which is really 0 degrees with respect to the normal. What's going to happen to it? Well, it is in fact going to reflect, but then some of it is going to transmit. Is that okay? So what happens when we go from one medium to another? Well, if we're a wave, one thing happens. Or I should say, if you're a wave, 3 things always happen. 1, we get reflection, right? 2, what else happens? We get transmission, right? Right? Part of the wave transmits. And 3, we get absorption, right? Absorbs. Well, we're not really going to talk about absorbs too much. We're really concerned about reflection and transmission. So this little section is just talking about the transmitted wave, which would be this wave right here. Well, what happens? Well, from last little lesson, we learned that when we go from one medium to another, the wave is going to hold on. The wave is going to change speeds. Okay? I almost said slow down. Well, I'm not 100% sure if it slows down yet, and it could speed up, right? So let's be generic and let's just say it changes speed. All right, well, how do I know if it speeds up or slows down? Well, that's got to do with kind of what we looked at last time, which was the index of refraction of the material, right? So here on our reference table, we have our sheet here, right? And this gives us our index of refractions, right? So let's take a look. What did I start off at? Believe it or not, I forgot already. Corn oil. So corn oil has an index of refraction of 1.47. What am I going into? Zircon, 1.92. So here I have an index of refraction of 1.47, and I have an index of refraction of 1.92. So what's going to happen? Well, we said that it's going to change speed, right? And with our little bit of knowledge now, we know that since I'm going to a higher index of refraction, right, my light is going to slow down. Now, once it goes through, it transmits through at that imaginary normal again. Well, let's see. Does it in fact slow down? Let's do some math. Let's just see, right? So how do I find out if what the speed change is, right? We're going to use our equation, n is equal to c over v. Now, I'm just going to do the math here. So what do I have? Well, you know what? Maybe I will do it. Let's just say corn oil. So corn oil, what do I have here? N for corn oil is going to be C over V. So what do I have? N for corn oil, 1.47, right? Speed of light in a vacuum, 3 times 10 to the 8th meters per second. And that, let's just call it CO, right? So what do I have? 3 second E8 divided by 1.47. So I get a velocity of light in corn oil of 2.05 times 10 to the 8th meters per second. So that's how fast light is traveling in the corn oil. What's going to happen when it goes to the zircon? All right, N is equal to what? C over V. So 1.92, 3 times 10 to the 8th meters per second times velocity in zircon. All right, so what do I get here? 3 second E, 8 divided by 1.92, and I get, we did that already, velocity in zircon, 1.56 times 10 to the 8th meters per second. So, right, it did in fact slow down. Okay, good. We know that when light goes from one medium to another, some of it transmits, and it's going to change speed. Sometimes it speeds up, sometimes it slows down. That's dependent upon the index of refraction for the two materials. Okay? So it's just a little recap of the last lesson. Okay? Now, I want to be specific here for a second. Now, let's look. I actually was very, very careful about what I did here. I drew this line coming in at the normal. All right, so what's going to happen, right, if I come in at an angle other than the normal? All right, let's just make stuff up. So let's say I have H2O, and let's say I have flint glass, okay? And let's say I come in at some angle other than the normal. All right, very similar to what we did when, oh, by the way, I got to pick some reference point, right? So just like I did last time, if I was going to draw reflected rays, right, I need to draw a normal, right? So right now, I'm going to draw myself a normal, right? Notice how I use my protractor and ruler to guarantee that this normal is, in fact, perpendicular, right? So let's draw an incident ray coming in, starting in water, coming into flint glass, and I'm going to say 30 degrees, right? So here is my ray of light, right? Starting, right, in water at 30 degrees, what's going to happen to it when it goes into the flint glass? Well, there's going to be a couple of things that are going to happen now. Well, first of all, you should say, well, it's going to change speed. The answer is yes. Is it going to speed up or is it going to slow down? Well, how am I going to tell? Well, one way to tell is just by looking at my indices of refractions. So where's my water? Right, 1.33. So an N is equal to 1.33. What's my flint glass? 1.66. Right? So hopefully, right, you're going to say, well, I'm going from a low index of refraction to a high index of refraction, so it's going to slow down. Well, let's take a look. Now, what I want to do is I want to answer a couple of questions here. I'm going to ask a couple of questions, and we'll take it step by step, and we'll see what happens. Okay, so first question, 1. Let's find, all right, speed of light in H2O and flint glass. All right, how am I going to do that? N is equal to C over V. We just kind of did this, so 1.33, 3 times 10 to the 8th meters per second. This is velocity. Let's call it H2O. All right, so we'll do a little bit of math here, right? So what do I got? 3 second E, 3 second E, 8 divided by 1.33, and about 2.25, right? So velocity in H2O, 2.25 times, my bad, 10 to the 8th meters per second. All right, how fast in flint glass? N is equal to C over V, 1.3, my bad, right? 1.66, 3 times 10 to the 8th meters per second, speed in flint glass. All right, so back to my calculator, 3 second E, 8 divided by 1.66, and I get 1.8, right? So a velocity in the flint glass, 1.80 times 10 to the 8th meters per second. Did I slow down? Well, I did, right? So I went from 2.2 times 10 to the 8th to about 1.8 times 10 to the 8th. So it did, in fact, slow down. So that's one question. What's one question answered? Do you know that I'm going to slow down? Okay, what's another question that I want to ask? All right, so I haven't talked about this yet, right? But I'm going to talk about it now. Another question that we would like to ask. What happens to the frequency of the light? Now, these are things that I would do in class with demos and stuff like that, but it's very hard to do here. Well, I had to just kind of tell you this. You just have to take my word for it. Well, what happens to the frequency of the light? Well, the answer is nothing. Okay? And this is just one of the facts that you have to kind of accept from me. Once a wave is produced, right, the frequency of that wave will never change. Let me say that again. Once a wave is produced, the frequency of that wave never changes. So what are the implications? Okay, if I am a wave, right? Here is my one equation that governs how a wave behaves. So let's take a look. What did I just say? Frequency never what? Changes. So this is always the same. All right, what does that mean then? What are the implications? Well, if the frequency always remains the same, and you know we just talked about light going from one medium to another, velocities can change, right? So the frequency remains the same. The implication is then it is the velocity and wavelength which change, right? And how do they change? Well, how are these two related, right? And what I mean is it a direct relationship or is it an indirect relationship? Well, let's take a look, right? As this gets bigger, what has to happen to this? This is also going to get bigger. As this gets smaller, this also gets smaller. So let's just take a look. Look what happened here. I'm getting ahead of myself, but I went from water to flint glass. What does that mean? Well, I went from a high speed to a low speed, right? So if the speed reduced and the frequency remained the same, what that means is the wavelength must change. The wavelength in this case is going to get smaller. So it's important to keep this in mind, right? Once a wave is produced, frequency never changes, okay? All right, if that's the case, right, let's take a look. Can we figure out, right? Can we figure out what the wavelength is in both, what did I say, H2O, right? And flint glass? Can I do that? Well, I think I can. Let's take a look. Let's just say H2O. So what's the equation that governs, right, my wave? Velocity is equal to what? Frequency, wavelength. Well, luckily, H2O, I already found out how fast the wave travels. 2.25 times 10 to the 8th meters per second, right? What's my frequency? All right, ready? Something else you got to know about this chart of the index of refraction. I don't want to get into it, but it's only good for one frequency, and that specific frequency right here. Don't want to get too involved with it. If we're going to use these index of refractions, which we will, one of the caveats is that it must go with this frequency. So, right, what is the frequency, right, for light in water? Well, it's going to be 5.09, right? So it's going to be 5.09 times 10 to the 14th hertz. So what's the wavelength? That's the wavelength symbol right there. Not a very good one. But what's my wavelength? All right, so I'm going to take 2.25 second E 8, and I'm going to divide that by what? 5.09 second E 14. And I'm going to get, looks like another pretty big number, but 1, 2, 3, 4, should say small number. 1, 2, 3, 4, 5, 6, 7. So my wavelength right here is 4.42 times 10 to the minus 7 meters. Okay, so what is your expectations about the wavelength of light when it goes into my flint glass? Well, since, right, the frequency never changes, right, and these two guys are directly related, I'm expecting my speed to decrease. I'm also expecting my wavelength to decrease. So what do I have? Velocity is equal to frequency times wavelength. And I think we said it was 1.80 times 10 to the 8th meters per second, 5.09 times 10 to the 14th hertz, because that's the frequency of light. Yes, it's going from H2O to flint glass, but once again, my frequency never changes. So let's see what I have. 1.8 second E, what did I say here? 8, right? Divided by 5.09 second E, 14. And once again, I'm going to get looks like a small number, right? And I know that it's going to be 3.54 times 10 to the minus 7 meters. And does this jive? Yes, it does, right? As the light goes from the water to the flint glass, it slows down, which means the wavelength is also going to get smaller. Is that okay? All right, so we've taken care of, what have we taken care of today, right? We've taken care of, you know what, looking at, right, little recap of my index of refraction. We've taken a look at, well, what happens when light goes at different angles. Well, I didn't really get into that yet, but we're going to do it in a moment, okay? I talked about what happens with the frequency, right? And I talk about what happens to the wavelength, okay? So I think that's a good place to stop now, right? But I just want to give you a little bit of a heads up, right? I don't want to get too far into it. I'm just going to draw this, sketch it for right now. Take an educated guess. Let's see. I'm telling you, I'm sketching out this drawing that I made right here. I'm coming in at a theta of, what, 30 degrees. What's going to happen? Okay, before, if I came in, right, at 0 on the normal, I go right through at 0. So it goes through in a straight line. Okay, what happens now? I'm not coming in at the normal. I'm coming in and I'm changing speed, right? This is what a straight line would look like. I want you to think about it. Make a prediction. Do you think that this light is going to continue on a straight line? Or might it, well, what else could it do? You tell me. Make a prediction. Think about it. We're going to look at this ray tomorrow, right? What happens specifically to this ray of light when it goes from one medium to another and changes speed, okay?